Get started today's CAN seminar. We are a little bit off on a Tuesday when we wanted to take advantage of a special guest who came up all the way from Vicksburg, Mississippi to be with us, and we wanted to definitely take the opportunity to bring him over and wanted him to tell us about all of what's going on down in the Army Corps of Engineers. This is Engineering Research and Development Center for those of you, ERDC, right? All right, so I would like to introduce first Dr. Tim Rushing here, Timothy Rushing, who is the Chief of Airfields and Payments Branch in the Geotechnical and Structurals Laboratory, GSL, U.S. Army Engineering Research and Development Center. So Dr. Rushing actually has his MS and PhD degrees from Mississippi State. He was telling me that he was working with Professor Isaac Howard, a friend of ours, and he began his early career then in the Airfield Payments Branch as a research civil engineer in 2005, and he's leading the Army's research efforts in the area of portable airfield mapping systems. I just heard his presentation a couple of weeks ago in Philadelphia at the ASC conference, and he's responsible for a multi-million-dollar research portfolio on that. He's a charter member and the Army Technical Representative to the Joint Airfield Surfacing Systems Technology Committee, whose mission is to promote collaboration and continuity among all DoD agencies using airfield mapping. So his first time to ATREL, second time to, I guess, Champaign.
That's right.
So there's an Army Corps of Engineers lab here. With that, I would like to welcome, and let's give a warm welcome to actually Dr. Tim Rushing.
Thank you very much, Dr. Tutumler. All right. Well, welcome everybody, and thank you to all of you for being here to listen to a little bit about the U.S. Army Engineering Research and Development Center and how we have involvement in specifically pavements and airfield pavements throughout the history of really the world. And you'll hear a little bit about that in some of my presentation. Like you said, you know, this is my first time to the university and first time here to the center, so thank you for having me. Looks like a great place, and all of you have a lot of wonderful assets and resources and professors and faculty to advise you. So I would say, you know, learn as much as you can, grow while you're here, and we hope that you guys will all be the next world experts in pavements and transportation. So we have faith in you, and we need you to continue to study and do what you're doing. So thanks to all of you for being here. So when I was thinking about a title for a presentation, I said, well, what might be of interest to the students? And I said, well, let's maybe talk a little bit about the past. You know, so there's some really interesting things that have come out of the U.S. Army ERDC. If I say ERDC, that's E-R-D-C. It's just a way Army likes to make a lot of acronyms that kind of sound like words, but not really. But that's what we call ourselves, as ERDC for short. So if you hear me say that, I'm just talking about our organization. But the ERDC used to be called the Waterways Experiment Station, the U.S. Army Waterways Experiment Station, or WES, because we like to have acronyms. But a lot of the things, if you're looking in literature for some of the history on pavement design, you'll see WES in a lot of places in the literature, and that's the same place. It's synonymous to the Engineering Research and Development Center. The ERDC was formed back in about 2000, where they combined a lot of different government laboratories into one organization, and all of that falls underneath the U.S. Army Corps of Engineers. And so try to put that into perspective a little bit for you. We're also going to talk some about ongoing research in pavements that we're doing there in Vicksburg, Mississippi, and some of our future challenges. You'll notice that this presentation has a lot of military flavor to it, if you will, because a lot of the things that we do is in response to missions that the United States military and our allies face. But these same principles many times transition into civilian applications over time as needed. And for an outline, I want to give you a little bit about an ERDC overview, who we are, where our organization came from, and how we fit into the Department of Defense. about our branch in specific, I am the chief of the Airfields and Pavements branch. I want to tell you a little bit about our organization inside of ERDC, and a little bit about the history, like I said, of airfield pavements and how that all began, some ongoing research projects that we have at our facility, and then some of our future challenges. And along the way, I threw in a couple of questions to ask you. So when I ask a question, I do expect someone to at least try to respond. So it's not just a rhetorical question thrown out there for everyone just to think about, but do kind of think about it and see if you can provide an answer. So the U.S. Army ERDC, Engineering Research and Development Center, who we are and where we are. I'm located here where this red core castle is, and that's in Vicksburg, Mississippi. We're located right on the bank of the Mississippi River. And in that location, we have 4 laboratories. We have Coastal and Hydraulics Laboratory that really studies the waterways, anything from ports and sediment transport, dredging, locks and dams and waterways infrastructure. Our Environmental Laboratory, they look at many different environmental cleanup things. How do we make our training ranges for our military safer? How do we clean up contaminated sites? And then all things that we do in research, they can go do checks and balances and make sure our engineering solutions are not harming the environment. Our Geotechnical and Structures Laboratory, that's the lab that I work in. There's 8 different branches, and the Airfields and Pavements branch is one of those in GSL. Information Technologies Laboratory, it's one of the largest computing centers for the Department of Defense, and they do a lot of research in computer engineering and computer science. And then here, of course, many of you may be familiar with our lab that's here in Champaign, Illinois. It's our Construction Engineering Research Lab, and so we do have facilities here in Champaign. And a lot of them take advantage of the research that you guys do and collaborate, and they produce, I think, many students with the university. Our Cold Regions Research Laboratory is near Dartmouth University in Hanover, New Hampshire. And then we have a Geospatial Research Lab over here in Alexandria, Virginia, next to Fort Belvoir. So it's a really large organization. From our our fiscal year 13 through 2016, we do about $1 billion average research within our organization among those 7 laboratories. And about 35% of that funding comes from Congress straight to us, but about 65% of that is reimbursable. And those words may not mean anything to you, it's kind of government talk, but what that means is a lot of what we do is like a consulting engineering firm. We have to go out to other members of the Department of Defense and help them with their problems to bring in that funding, just like a university does. So we're not just given money to do our research. We actually have to understand our customers and what their issues are, and then propose research ideas to them. Customers, who do we work for? You know, we don't generally work for universities or for private industries that often, although we do in some cases. But we work for a lot of the different agencies within the Department of Defense. The Air Force, the Navy, the Army, the Marine Corps, the Department of Interior, Department of State, the National Science Foundation. So a lot of these big government agencies that you've heard of, these are the people that we work for primarily. Our demographics, we have now, it's really up to about 1,200 engineers and scientists within the ERDC. And then we also have a large technical staff and a lot of technicians who actually support and carry out a lot of the research that we do. You know, degree-wise, about 1/3 of our folks have PhDs, and the rest of them will have one within the next 5 to 10 years because we've highly encouraged them to go out and get their PhDs. In fact, we like it so much that we will pay them to do so. We have a long-term training program, so when people come in, they can go to a university of choosing. A lot of them have come here to the University of Illinois, and the government pays for their salary and all their tuition and everything for that year to take all their coursework, and then they come back home and do research and graduate in 3 to 5 years. And that's the plan. So I just did that. I completed mine last December. So after I've been with ERDC for 12 years, and I had a bachelor's degree when I came in, and so I got my master's and PhD while working. So it's another great opportunity that ERDC offers folks. And so we are here in Champaign because we're at the career fair, the Engineering Science Career Fair, today and tomorrow, and we are hiring. ERDIC is making a push to hire about 400 engineers and scientists over the next couple of years. So if any of this sounds interesting to someone and something you would like to talk to us more about, please feel free to come talk to us at the career fair. Academic affiliations, of course, we are certainly affiliated with the University of Illinois. We have students that come from our lab here at Searle, and then Searle also hires a lot of students to do internships and summer work and such. We do the same thing in Vicksburg. We hire probably 150 students from all over the country in the summertime. There's several different programs for people to come in and do research during the summer or whenever they're available. We also have a graduate institute in Vicksburg where we actually take classes on our own site, and people can we can take virtual classes through Mississippi State or Texas A&M, and then we can teach classes, and students of those campuses can take them as well. Business areas, primarily are the areas that we work in and do research in are military engineering, geospatial research, environmental quality, and civil works. When we say civil works, that's more your traditional infrastructure type research for the Army Corps. And then military engineering, the main places that we work in are protection, understanding and developing how to protect against weapons effects, force projection, how do we get from where we are to where we want to be. That's where a lot of the airfields and pavements works comes in. And then maneuver, how do you get a vehicle maneuvering across a rough terrain or a terrain that's not that passable. And so understanding the geophysics and the way that soils interact with vehicles is very important. And then we also, another neat feature that we have a reach-back center at ERDIC. So soldiers, airmen, Marines, people out in the field can call us, and we can use direct communications back to subject matter experts to help them with any kind of engineering challenges they have. And so that's open 24 hours a day, 7 days a week. And so we're constantly fielding calls back from the field. Okay, now shifting gears just a little bit. That's kind of a big picture of who we are as an organization. But our Airfields and Pavements branch, because no one else is in the room, and I'm sure this is not being recorded, we are the best branch in all of ERDIC, the Airfields and Pavements branch. Oh, this is being recorded? Oh, sorry. But you can see with some smiling faces, we do a lot of great things and have a lot of fun. We have some great people. And I'm not biased or anything being the chief of the Airfields and Pavements branch, I promise. Our people, so fun stuff, Airfields and Pavements. We have about 42 federal employees right now, and then 5 more contractors, so close to 50 people. So it's fairly large organizations in terms of a branch. We have 9 folks with PhDs, since I finally got to add mine to that list. I know some of you guys are probably ready to add yours to a list that says you have a PhD too. 13 master's degrees and 3 bachelors that are working on master's degrees. And several of our master's degrees folks are working on their PhDs. So we expect that number to grow. 25 of our folks are scientists or engineers. So a lot of people looking at different types of pavement problems. A couple of unique facilities that we have. It's kind of like you have here for accelerated pavement testing. Accelerated pavement testing is something we've been doing in our branch since about 1942. And we've done that through different types of load carts and load vehicles to now we have the second largest HVS A for airfield or aircraft in the world, because the FAA bought one and they made theirs about a foot longer than ours, so they could say theirs is the largest in the world. So yeah, well, if we get another one, it's going to be a foot longer than theirs, I promise. So we kid each other about that. But theirs is just a little bit bigger. But our HVSA is really amazing. If you look down here, some of the stats on it, it's the second largest in the world, I have to say. But it can go up to 100,000 pound loading capacity. So that's pretty big, right? I forget, Dr. Alcati, what you said your load capacity was.
I didn't mention that to you, but it can go up to 60.
Okay. So yours can go up to 60, but it's normally around 40, but this one can go up to 100,000. So it's really big. It takes a lot of load. So it has a giant reaction frame. You can't see greatly in this picture, but that big steel structure is just so when you push down that hard, it doesn't lift up, right? But the nice thing is, and probably like yours here too, it can run 23 hours a day. We take it down 1 hour a day just for maintenance and check everything, make sure everything is going well. And so you can put 20 years of aircraft traffic on a pavement in just a matter of a couple of months. So that's really nice to know when we're trying to do performance studies or validate our criteria for airfield pavement design. And then also, just like yours, we also can do climate control testing. So we can do cold pavements in the summer and hot pavements in the winter, or normally we keep it at like 77 degrees Fahrenheit, so we have a constant climate during our testing. Because one thing we certainly found, especially with flexible pavement, is if you have a lot of temperature variability, that's researchers sitting here and doing this when you look at the data, right? Like, well, was it caused by changes in the temperature? When I tested this test section, it was this, and this one, it might have been a little bit different. So one of those variables that we like to take out, especially on viscoelastic materials, is temperature, right? And so that's the reason that's very important. We usually don't study so many effects of hot or cold pavements. It's just keeping it consistent. And in this, we have this giant facility that is here. It is our Hangar 2 facility. It's 127,000 square feet, so you could play a couple of football games in there at the same time. And it was opened again in 2015. We were given that hangar. It was an old hydraulic model, and they refurbished it for us, and we moved it, had to clean out a bunch of old hydraulic models and turned it into our research facility. Prior to that, we had a structure called Hangar 4. And so if you look through a lot of the old history records and things that we did at Wes, you'll see Hangar 4 referenced a lot. This is the same type of facility, only it's a little bit longer. They had to tear down Hangar 4, which I did literally shed several tears over, because they had to build a brand new ERDC headquarters building in the middle of campus, and it was right in the middle of campus and it was in the way, and they told us it had to go. So we have a pretty new facility now, but it's very nice. We have offices and maintenance facilities and all undercover. We also, just like out here, we have a big area, just an open space that we do outdoor testing. We do a lot of pavement repair research, and so you need a lot of space, places you can have big heavy equipment make a lot of noise, and so we have a facility for that as well. One other thing we also built out there is kind of nice is we do structural evaluations for airfields and railroads for the Army, the Air Force, and some for Defense Logistics Agency and the Marine Corps. We have some calibration pads, one for our ultrasonic testing equipment for rail, so we can look at internal defects. So we purposely put defects in a bunch of rail sections so we can make sure our equipment's operating properly. And then we have a concrete section that is used to calibrate our falling weights and our heavyweight deflectometers. So that's kind of a neat thing we added in the last few years. Okay, so full-scale pavement sections. How many of you have been involved here with building any of the controlled sections? Several of you have, so that's good. That's good. So you'll know everything there is about how that happens, right? I see Dr. Tutumor smiling back there, but this is what we do. This is what the ERDC, the Airfields and Pavements Branch, has been doing really since the 1940s to try to understand the effects of loads on a pavement section, and then also to validate criteria that's developed, right? So we don't know if it works until we go load it. But we go in and remove the subgrade. You line it with plastics, and why do we line it with plastic? Is that weird to line it? Anybody have an idea why you would line it? Why we line it? That's right. You don't want the moisture to migrate into and out of your sections because, especially in the subgrade, we want to try to keep that moisture constant because these tests, do they happen fast? No. Normally, at least it takes weeks would be fast. Normally, it's months when you're doing a controlled, accelerated pavement test. And so you're worried about changes in the moisture content or the strength of your materials in that section, because what happens if you don't protect it, you get strength increase or decrease depending on the conditions it's facing. And then again, there's more variables that you have to worry about and try to figure out where the deviations came from. So we line it with plastic, and then we use a material that no one on the face of the planet other than pavement engineers would ever want. And it's this horrible stuff called Vicksburg buckshot clay. It's a high plasticity clay material. It's nasty, gooey, sticky, yucky, whatever kind of engineering words like that you want to use. But the great thing about it is it's one of those great clay structures that really loves water. So it's the sheets of paper with the water molecules between it, and it won't let them go. So once we get a moisture content to a place we want it, and we've got a lot of curves that have been developed on moisture content versus CBR. So once we get the moisture content right, we know what the CBR is going to be. We go in, we process it to get the moisture right, add or take water away and let it dry, put it in place. And our guys have been doing this for so long that normally, especially on the 3 to 6 to 8 end of a CBR, they can get this right on the first or second try. Putting in a giant lift, 6 to 8 inch lift of this buckshot clay in, compacting it, and they know how much moisture they're going to lose based on the temperature, how much sun is shining on it, all those things. They're really experts at getting the soil just right, putting it in place, running a field CBR test. All of you done that, right? Some of you are kind of nodding your heads. Others are like, I don't know what you're talking about. Not a lab CBR test, but an actual field CBR test. Run those, checking that, make sure the soil is plus or minus a half a CBR what we want, and then we do it again. And so we'll build everything in 6-inch lifts and checking the CBR all the way up. And once we're confident that we know what that strength is, then we'll go in and put our subgrade or our pavement layer or base layers. Your subgrade and your base materials, normally you don't have quite as much issue with variability in strength over time. It does change, but the subgrade is the most important. If we're doing a mat section, like in this picture, we just build the clay section and put a matting panels right on top of it to simulate a very soft condition. Well, I'll talk more about that in a minute. Okay, so now for the military, kind of thinking military, how do you define a pavement? You think about pavements and all the things that we learn in school, and normally we're talking about asphalt concrete pavements or flexible pavements. We think about PCC, Portland cement concrete pavements or rigid pavements. What else? What else is a pavement?
A layered structure.
What's that?
It's a layered structure.
A layered structure?
To carry traffic.
That's right.
Composite pavement.
A composite pavement, that's right. There's a lot of other things, but for us, sometimes the military doesn't have the luxury of having speakers that don't fall over, excuse me, nice structures to operate on. Webster says the definition of a pavement is a paved surface such that artificially covered surface of a public thoroughfare, the material to which something is paved, so that's, or something that suggests a pavement, which is as in flatness, hardness, or extent of the surface. So really the definition number 3 is closer to what I'm thinking in terms of a pavement for the military. So a lot of times a pavement for us may be dirt, it may be a farm field, it may be grass, it may be a portable matting surface that's a bunch of aluminum panels stuck together and assembled in a big mechanical system in a tire airfield, and we put it down. So for us, there's a lot of different things that constitute a pavement that aren't really quite textbook, and we don't have textbooks written on how to operate on airfield matting systems, for example, or how to design them. Some of the large cargo aircraft that the U.S. military and a lot of our allies have and around the world they're designed to operate on dirt. But we don't have as much guidance on airfield design for unsurfaced aircraft outside of military operations. We do for smaller planes. You've got bush planes in Alaska that land wherever they want to land all the time, right? but looking at design criteria and design perspectives, that's a kind of a different way to look at it. But any open flat space may be an airfield or maybe a pavement to the military. And so those are some challenges or different things that we have to consider. So again, I wanted to talk about, okay, so where did all this come from? So we in the, at the URTIC have been doing pavement and especially airfield pavement design from the very beginning. It's kind of different to think about where this came from. I was very intrigued last night. We have a book that was written back in around 2000, maybe a little before. There was the history of geotechnical engineering at the Waterways Experiment Station from 1932 to 2000. It was a very interesting book, and I actually learned some things that I didn't even remember just by reading through it last night. We'll go into some of those things, but when we started, the branch that I'm in, the Airfields and Pavements branch, all started out of necessity, and that's the way a lot of things happen with the military. As you find a challenge, you need to address or overcome something, and so you become very innovative very quickly out of necessity. And so that's kind of how the Airfields and Pavements research and airfield pavement design was born in the very beginnings. No one said, hey, the Wright brothers flew an airplane, we need to start thinking about pavement design for airfields, did they? No. They were landing on grass. They were tiny. It didn't matter. Sodded fields were fine. It wasn't really until the lead up into World War II that aircraft started being used as primary weapons of war, and there was a push to make them bigger, faster. So people started really ramping up production of designs of larger aircraft that suddenly got much heavier than our automobiles of the day. So it was kind of all born out of necessity. These are kind of a couple of cool pictures from about the 1950s of early simulators. If you come to our site today and go in that hangar, you'll see vehicles that look just about like this. They haven't changed a lot. This old scraper engine wore out, so we bought a new one. And this old truck, probably they finally got where they couldn't make it run anymore, so we got a new one. But in general, the concepts of putting lead blocks or steel blocks on a vehicle with a aircraft tire and wheel on it to simulate what that actual load was. And then this one, they put lead blocks in a box like that with a full multiple wheel gear assembly in it and pull it with a scraper. That's still how we do things today, other than our HVSA. So these are just kind of some neat old pictures from our. So this B-29, that's kind of a famous aircraft for us in airfield pavement design history, because this is the literal straw that broke the camel's back, or the one that was the wake-up call that said, yeah, this matters. That's the aircraft there. This picture shows some metal planks being installed. That's PSP, or pier steel plank. That mat system was one of the first matting systems or temporary surfaces designed by the United States military, and it was so popular that they built over 900 million square feet of it between the 1940s through the 1960s and into the early 1970s. That's a lot of square feet of metal, a lot of it. So that was a very successful system to be able to go for our military to support operations anywhere, anytime, and go build an airfield. So it's a pretty interesting concept. And oh, by the way, I haven't found any others, but I may be the only one there's ever been, or may not be another one, a person who got a PhD in airfield matting. So just another little fact. And this shows just kind of an early example of an asphalt pavement apron with some aircraft. All right, so in 1930, the U.S. Army Waterways Experiment Station West, now URTIC, was built in Vicksburg, Mississippi. Does anybody know why the Waterways Experiment Station was formed? There was one big event in U.S. history that caused this to happen, other than Dr. Al-Qadi. All right, so in 1927, something important happened to our nation. we had a historic flood on the Mississippi River, and it caused a lot of damage. A lot of property was lost, a lot of lives were lost. It was a big problem for infrastructure in the United States when the river got that high. And so because it flooded, the federal government said, and the Corps of Engineers said, we've got to understand the river and how it operates. We've got to understand how do we protect ourselves against it, and how do we design levees that can hold back that volume of water and protect our people. And so there were a lot of discussion went on, and at the end of it, they said, we're going to build this in Vicksburg, Mississippi, right there next to the bank of the Mississippi on a high bluff that won't flood. So we can do our research there, and that's why Vicksburg, Mississippi was the beginning of this. Had nothing to do with airfields, right? Nothing to do with pavements. It was a bunch of geotechnical engineers and geoscientists that really understood soils were brought to Vicksburg to really start studying the river and how to protect our nation against its effects in case of major flooding. Incidentally, that record, 1927 flood mark, has only been broken one time. Does anybody remember when it was? All of you were born, by the way. I think, yeah. It was just a few years ago, right? In 2011. The Mississippi River broke that 1927 record, and there was not catastrophic flooding. There was not a bunch of loss of life. There was still some flooding, but the system held. That system that was developed because the Waterways Experiment Station was established, and those guys figured out how to tame that river. It worked. Now, the other interesting thing is, to do so, there was something that some people that lived in the area didn't like. There's an area that's a floodway, and Congress said, if the Mississippi River hits a certain elevation, then we are going to open this floodway, and we're going to flood a big area of land to take the pressure off the levee system so that it won't fail. And the Corps had to do that. They didn't want to do that. Nobody wanted to flood out a bunch of people's homes and farmlands, but the people that were living there were told it was going to happen. But if the water ever get there, but they felt that it wasn't ever going to do it again, but it did. And so the Corps had to go in and blow the levee open, allow the water to flood this area, and then blew it open again downstream to catch it and let it come back in. And it worked beautifully, just as designed. So it's pretty interesting aside, but the ERDC was involved in doing a lot of that work as well. So it's pretty cool. So anyway, getting back to pavements. The place was formed in 1930. In 1936, have any of you ever heard of Arthur Casagrande? I hope most of you at least heard of him, right? He's one of the leaders in geotechnical research for the nation. That's right. The thump, 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 and the shear and the direct shear test and all of that stuff we can contribute to Arthur Casagrande. Well, he established a relationship with the Corps early on during all of this, but in about 1936 he really was a key player. And in the Geotechnical and Structures Laboratory at ERDC, where I work, when I walk in my building, it says the Arthur Casagrande Building. His name's big. There's a big portrait of him right in our lobby when you walk in. He meant a lot to the Corps and a lot to the way the world looks at pavements, believe it or not. And so he was a very key leader in that field, of course. 1939, the Army Air Corps came out and said, all military aircraft, except for our loaded bombers, which weren't that heavy at the time, would be operating on sodded fields, so we don't need anything to do with pavement design. That's not important. And that all worked great for about a first year. Their assumptions worked until they came out with that B-19 bomber that I showed you a picture of. They rolled it out of the assembly line ready for its first maiden voyage, this experimental bomber plane. They rolled it out onto the apron and it broke straight through the apron. They said, geez, oh my goodness, well, we got to use this thing anyway. So they got their tugs and they taxied it out on the taxiways. And guess what? They probably, I've seen a picture, but they probably rutted, several inches deep and just tore it to shreds. And then when they got it out on the runway, it did the same thing. And they said, oh my goodness, I guess we do need pavement design that's different for airfields. This does matter. Let's do something about it. And so, because it's an emergency now, right? We're ready to use these big airplanes for weapons of war, but we can't use them because we don't have pavements to operate on. there's a theme here for pavement design that I want you to remember, and it is that we as engineers are too good to the world. We let our aircraft or our vehicle designers design whatever they want, and then we fix it. I'm not sure if that's a good thing or a bad thing, but they never ask us on the planning stages or design stages, do they? No. They come back to us and say, fix this problem. Your pavements won't work. My airplane's so big it's tearing up your pavements. Get new pavements. And, you know, so it's like, talk to us on the front end. We can help you design your aircraft that won't tear up our pavements, right? That doesn't happen. So anyway, you'll see this lesson continues to be repeated through history, but we civil engineers always save it for them and make their airplanes look great. Like I said, I'm not sure if that's a good thing. Maybe we should let them fail. They'll listen to us. But nobody ever thinks about the pavement until it's too late. So this is where it all started. So in 1942, after 2 years later, Wes was feverishly working on understanding how to build a pavement structure that can support these massive aircraft. 160,000-pound airplane. Of course, now that's tiny today compared to some of the aircraft that we're operating. The C-17's 585,000 pounds. I know that one by memory. I don't know all the rest of them. C-5 is bigger than that. So we have a very, very heavy ones. But 160,000 pounds compared to these 12,500 pound single wheel loads, so that's probably about a 50,000 pound plane, was significant. So we came up with a CBR method for flexible pavement design. Took us a while, but we did. And so that method actually is used from the 1940s through almost today. You know, we've changed some now, but through a long span of history, the world used the CBR method of pavement design for airfield pavements. And that was started right away. The flexible pavements branch was established at Wes. And we also, I did not realize until I read this last night, but the modified Proctor lab procedure was developed in the laboratory in Vicksburg, Mississippi, to account for the effects of aircraft loading on soils. So before that, we used the standard Proctor and said, hey, this is not giving us the compaction and density that we need. So they modified it. They just got a bigger hammer, raised the drop height, and called it the modified Proctor, and we still use it today, right? Pretty interesting. So that was all done in 1942. Another interesting thing I read about, the Army came out right away and said, we're going to use Portland cement concrete for all airfield pavements. It's strong, it's tough, it can handle aircraft, we can just make it thicker. Great, except for the feasibility of really doing so is not cost effective, the materials weren't available, the time it took for construction, all of those things. The Waterways Experience Station researchers said, no, we can't just stick there. We've got to have a flexible design procedure, and so that's where that was born. And then other really interesting, cool thing for pavement folks, Wes hired a guy named Bruce Marshall. Anybody ever heard of a Marshall stability test or a Marshall mixed design procedure for asphalt? Bruce Marshall, he worked for the Mississippi Department of Transportation. And he came up with this way to modify a CBR apparatus to do an asphalt stability test. And he basically got told, yeah, that's great, but go somewhere else. And so he did. And he went to Vicksburg, and he talked to his colleagues at Wes, Waterways Experience Station, and said, hey, look what I've got. I've got this apparatus. We can use it to do a stability test on asphalt mixes. And so what did Wes do? They hired him. And so he developed that, and it became the standard for all of the paving industry, the things that Bruce Marshall came up with. And so that all also happened in Vicksburg, Mississippi. So moving on through history, you know, I told you that we had to chase airplanes. Well, you'll see a theme throughout our history of our branch that we've chased airplanes. Trying to keep up with the airplanes is mostly what we've done. But design and construction criteria for the B-29 and establishing these landing mats. These landing mats were critical too because we needed a way to carry pavements with us. We're going to go stage tens of thousands of aircraft over in a European theater, and we can't just go park them on dirt and know they don't have time or the capacity to go build a bunch of parking areas for airplanes. So we needed a way to do that. If we put them on grass and it rained, they were going to sink, and then we'd have a mess. So the Corps of Engineers said we need a portable system for pavements. So they came up with this pier steel plank concept. I told you had 900 million square feet of it built. That's crazy. It's a lot of stuff. And it worked great. And so all of those systems were tested in Vicksburg in our hangar under simulated load carts to make sure they would carry the loads of the planes under different CBR strength conditions. And we have continued to do that research and been pretty much, I think, the only ones in DoD that have ever really done so successfully throughout history. We're still working on that today. Like I said, I had a PhD in airfield matting, so that one subject I could probably talk to you for 2 hours on, but I won't. I'll stop myself. But just know that the military does have portable pavements. We have things that we can pick up and carry and literally build an airfield anywhere we want to. And so now we're looking at lighter weight materials and how do you maintain the structural integrity and the modulus of the system, but make it lighter so we can take it more places easier. So that's also been a theme through history. Then we started getting even heavier. Again, landing mats continued, pavement design transformation continued. We started looking at evaluating our pavements. Have any of you had classes in pavement evaluations? Doing the PCI surveys, back calculations? Yeah, so a lot of you have. Falling weight deflectometers and all QOBs and such. All right. So a lot of you have familiarity that all that started back in the 1950s and 60s. We have reports from doing pavement evaluations from the early 1950s. And so it's been very important for us to understand the condition of our airfields and how do we evaluate them. So in pavement evaluation that started there, when we got into the 1980s, we started having companies like Dynatest and others developing equipment that said that we could use it for non-destructive evaluations. Why is that important? Before that, what did we do if we wanted to know the strength of our pavements? Does anybody know? Not just cores, much worse. We had to do plate bearing tests on every layer in the runway. And you had to cut like a 3 foot by 3 foot by 3 foot hole, and you had to run plate bearing tests on every single layer to understand what the K value was to be able to determine the strength. Now, you can imagine you can't do a lot of those, right? You can't go every 100 feet down a runway and run these and tear it apart and run plate bearing tests. So how good was our answer even when we did this? It was really good for that one spot, but the spot over there may not have been so good for, right? So you get a lot of variability in that data. The strength profile of a 10,000 foot runway does this, right? It's all over the place. If any of you looked at FWD values of a road or whatever, it's not a straight line. It's all over the place. And we designed to our weakest section normally, right? So the problem was with the destructive testing, you missed a lot of stuff. And so we would have failures where it would be fine in the area we looked at. But the other problem was we had to shut a runway down until we could finish our test and repair it. We couldn't get out of the way. So point being, non-destructive testing was a big deal, especially to the military. It certainly also was for commercial aviation. And so a big study was conducted by the Corps, or the ERDIC Waterways. They called it the Great Thump Off. Kind of catchy for pavement engineers, right? Dropping weights on pavement. Great Thump Off. So they looked at all the commercial systems on the market. They looked at a thing called a 16-kip vibrator. It was more of a larger system that just shook the pavement and measured the response. And they looked at many different other types of falling weight deflectometer devices, and ultimately chose for the Department of Defense to use the Dynatest type of equipment. And so that's still what we're using today. But that was a big deal. That really gave us a lot more, we could do a lot more tests on our airfields. We could get out of the way in a minute's notice because it's just being a trailer pulled behind a truck, and we had a lot more confidence in our answer, right? And we could find out where there were areas with voids or weak spots, and we could go repair those and improve the compatibility of our airports. Also, our layered elastic design procedure was developed in the 1990s. We've stood up now not only airfield evaluation programs, but also a railroad evaluation program. So like I said before, we go out and do rail inspections and evaluations for a lot of the DoD. And then as you move into today, what are we doing? 3D finite element methods for design. We've got advanced materials characterization, and continuing along with our PK software that's our back calculation program. I think I've got a slide on that. And then more contingency operations and repair. Recently, a lot of what we've been doing is rapid pavement repair evaluations and modernizing. How do we go out and get an airfield that's been damaged open very quickly? Okay, so shifting gears from the past to where we are today. So what are we doing today? Airfield pavement evaluation program we talked about. We have over 51 airfields around the world that we evaluate for the Army. Our PCASE is our structural analysis and evaluation software. It's not, the neat thing is not the software. The nice thing is it's just a GUI. The neat thing is all of the DoD specific criteria for design and evaluation is embedded in this GUI, so that anything that comes out of it we know is designed by our specifications and standards. So this is where all the DoD guidance and criteria is housed, which is a little bit different from commercial or FAA criteria. And airfield repair. Okay, so here's another kind of question. So here's our challenge. This is something we've been working on for a while. We've got a large hole in the middle of your runway. It's 10 to 20 feet in diameter. Don't know how it magically appeared, but it's there. You don't have much equipment. You've got to get this thing back open so airplanes can land on it again in 4 to 6 hours, and you're going to have heavy cargo aircraft, these 585,000-pound ones, and you're going to have 400 PSI tire pressure, single tricycle gear type wheel loads on it. They weigh 40,000 pounds, very concentrated loads. So bottom line is this repair, or whatever you do to it, it's got to be strong. And you want it to sustain about 3,000 traffic passes, and so what do? Simple, right? No, not at all, right? So these are the types of challenges that we get to face as pavement engineers who work in military applications. What do we do? And so this is something that we've worked on for about 10 years now. We've been working on it for a lot longer, but we've been refining, modernizing this capability here in the last 10 years. So we've got to open an airfield in 6.5 hours. Now I said 2 to 4 before, but the 6.5 is from going assessing damage to removing the damaged pavement to repairing it. And so the things we're looking at is a lot of the new rapid setting concretes. We've done tons of research on those materials and really understand their performance. We've developed a certification program because there's a lot of things on the market, and to make sure that the products are good and meet our needs. Flowable fills or more of a lean concrete material, something that is excavatable later, that sets up rapidly. The neat thing about the rapid setting concrete that we're using is you can put any traffic you want to. It's over 3,000 PSI within 2 hours of placing. That's pretty impressive. The rapid setting flowable fill, we can put it in as what we call the slash and splash method, which I really like. So you can slash the bag open, the dry powder goes in the hole, you can splash some water over it, no mixing required. The water self-permeates, and you can walk on it within 20 to 30 minutes, easy. And so within 30 minutes, we'll place the rapid setting concrete over the top of it for a structural cap, and 2 hours later, you can be flying. It's pretty impressive. So that's the method that is kind of our go-to standard if you have the materials available. Other really cool things that we're still got to work on some refinement. Rapid expanding urethane foams. That's pretty cool. That's kind of out of the box thinking. You've got a material that can expand 6 to 8 times its volume. That's a big deal. You don't have to transport nearly as much material with you, and it has a roughly equivalent of about a 30 to 40 CBR. So it's pretty strong. So you can squirt some of this liquid stuff, like the guy on a Christmas vacation, put it in the hole, you calculate your volume, it'll rise, and then you put your rapid setting concrete cap on the top, and then you've got a pavement that's ready to traffic. So some pretty cool things. Other interesting things, the slowest part of all of it is removing the damaged pavement, especially sawing around it. So as all of you know, that's very important to have square edges, right? You've got to saw your repairs out. Don't ever do like the county guys that repair our potholes, where you just shovel some stuff in it. No. Cut it square, dig it out nice and clean, put the material back right, in the right thicknesses, maintain your joints if it's PCC. Pavements, don't lock up your pavements. You know all those things, right? Never, ever, ever would do that wrong. Says we need to make sure we have people that do it right. Because the worst thing is to repair or repair to repair or repair to, you know, over and over and over because it's done improperly. All right, so I won't get on that soapbox. But anyway, so it's really cool. I've got a little video. If I click this, it's supposed to play. It's going to show you kind of the process. If you'll look here, I don't know if you can see, but those little white-looking marks are spalls or damaged area on a pavement. And this is going to quickly go through some of the sequencing of how we repair an airfield, and then it'll show a C-17, the big cargo aircraft, landing on it as a validation that it's safe to do so. As you can see, assessing the damage. That was when they sliced that bag, was the flowable fill. A simplified volumetric mixer that has pre-blended material. You just pull the chute, the dry and the wet mix, and places it. And then this is the guys just getting ready for monitoring the traffic and sweeping the airfield. And then the C-17 comes in. So if it could happen that fast, that'd be really awesome. The video is cut out a little bit, but that kind of shows you very quickly the process from everywhere from you got a mess on your pavement, you cut it out, you remove it, you put that flowable fill that's rapid sealing the bottom, concrete on top, and you're good to go. And it will sustain over 3,000 passes. Evaluation of warm mix asphalt, that's not new. But what is new is developing criteria to be able to use for DoD airfields. So we ran some tests, and now that's been put in criteria. We've done a lot of work recently on pavement preservation. I've gone out to several different Air Force and Army installations and put down different surface treatments, and we're doing a long-term performance evaluation on there to see which products in different regions around the country work best, so we can make recommendations, and that's been finished. Looking at different methods for non-destructive determination of pavement thickness, anything from the Mira device for concrete pavements to different types of radars. We're always looking for the next complementary piece of equipment for non-destructive testing. Materials processing, again, on the matting systems. This is looking at how do we better design our pavements to make them lighter weight, using additive friction stir processes to join dissimilar alloys to improve fatigue critical components. Looking at a lot of different things there. A lot of geosynthetics research. Dr. Tutumler is working on some of these projects with us for the FAA and as well as the Air Force, looking at better ways to, or how, really more of an understanding of how these systems perform within our pavement structure, where to put them, and then how much improvement in performance do we have when we put different types of geosynthetic products in pavements. Precast concrete panel repair. That's another method. If you have a critical part of infrastructure you know you may have damage, can you have precast panels ready? And then how would you do the procedures to install these and use these for repair? This is another really interesting. We hired a physicist in our pavements group. I don't know what to do with him yet. Really nice guy, really smart. But we found out one thing really cool. He actually is really good at writing apps and computer code. And we gave him a friction project. We said, well, this is a good thing for a physicist, and he's really done a great job. He's came up with the fact that there are little MEMS devices and accelerometers in every one of our smartphones. And can you use those, not to get an accurate friction value, but can you use those to get a good enough reading, and I call it, from a layman's point of view, a red, yellow, green rating on whether or not you have friction issues and need to do rubber removal. So you can get the airfield manager who's responsible for the runway to take his phone and stick it on a Velcro thing in his car and drive down his airfield and slam on the brakes multiple times and with this little app running, and it can give him, turn his screen red, yellow, or green and let him know whether green, the friction profile's fine, you don't have any issues, or Yellow, which means we're not sure, but you probably ought to come out and have somebody do a real test to get a real friction value to check. Or red is, oh, this is too slick. We've got to do something about it. So it's a pretty cool project. Just to take, he bought a whole bunch of smartphones, and I said, what are you doing with all these smartphones? And he just wanted to try every newest make and model because he was really just testing the accelerometers and the coding of those accelerometers. It's pretty cool. So that's what we're doing with our physicists so far in pavements. No, but he's great. We got more to come for him. Joint and crack sealant testing, we actually have a laboratory stood up just to look at joint and crack sealants because DOD, and I know all the DOTs, spend an exorbitant amount of money sealing cracks and sealing joints. And if you don't have good products, you're wasting a lot of money. And so that's a big deal, is to get those materials certified, make sure they work. And, concrete coatings and a couple other interesting things we have these weird transformer aircraft, the Osprey, and it causes damage to our pavements when you put heat on top of fuel. It actually causes damage to our PCC. So we're looking at different coatings to prevent that. Non-nuclear density studies. Even the military can't pick up a Troxler gauge and throw it in the airplane and fly it around the world wherever we want it. So we need another way to do that. So we did a study and we really found the Troxler's E-gauge, which is not non-nuclear, but it's so low source nuclear it doesn't have to be permitted, was the best one. And so we've studied a lot of those. Point cloud analysis of surfaces. We're looking at photogrammetry and LiDAR to be able to do things like what is the condition of the pavement in terms of like PCI, or what is the damage in the pavement? So how can we go quantify and characterize all the damage in a pavement using photogrammetry and LiDAR in unmanned vehicles? And then updating the matting criteria, dust abatement, and then many other things, unsurfaced airfields, marginal materials, rapid ways to analyze soils. We have little backpack kits you can jump out of airplanes with, do halo jumps and all that good stuff. New AC patching materials. How do you do hot mix without having hot mix? It's kind of interesting. Anchor systems, again, railroad evaluations, geocomposite drainage layers, tack coats, all kinds of different things that we're still looking at. So, almost out of time. That's why I'm moving faster. Finally, vertical takeoff and landing. This is a new thing. A lot of you have seen this F-35 awesome new aircraft. So here's another challenge. We've got a new airplane. We're chasing airplanes again. It causes extreme heat when it's landing. It's coming down. It's got that engine nozzle. It melts asphalt concrete and causes the particles to get loose and causes FOD, which is foreign object degree. Bottom line is it can tear up an engine. And then the Portland cement concrete just centers, powderizes, and you get FOD or rocks loose, larger aggregate loose there. And we can't land on dirt for the same reason, so what do? How can we operate this airplane? Another thing, they didn't ask us, right? They didn't ask the pavements guys. They'll fix it. Civil engineers will solve it. You know, we just built a cool airplane. Y'all tell us where we can land it. So what do? So for right now, this is the F-35B variant that's landing vertically. And if you can see a little bit of a green color right there, one of the things I got my PhD in was what? Airfield matting. Our airfield matting planks are aluminum. We don't melt it. We can operate on it safely. So all the operations, vertical operations so far ever done with that airplane have been done on an aluminum pavement system. Right? So pretty cool. Glad we had it. Wasn't designed for it, but it sure does work. So some of the challenges that we face, you know, anything from our unmanned vehicles getting bigger and bigger. Look at the size of the wheels on these things. They're like wheelbarrow tires. They're tiny. So roughness matters. That's the key there. That can be a problem. Of course, unsurfaced operations of these big giant aircraft. How do we understand what is the conditions like? Can we land? Can't we land? Is it too wet? Is it too dry? The tilt rotor aircraft are just strange, right? And all kind of crazy load applications from all the rotor wash is what's really unique. Heat resistance. This one was really cool. Infrastructure construction in a quagmire. I didn't even know that was a noun. Had to look it up. It's like, what's the definition of a quagmire? It's actually a boggy, marshy area that's soft underfoot. It's a noun. Who knew? So yeah, things like this is what we have to make roads out of for the military. So a lot of challenges for pavement engineers working for the military. And so that's all I really had on pavements. This was another really interesting challenge because I knew there was a rail center here and doing rail research. This is a real one. I need an answer. So if you can get with me after class, let me know. But we've got aging infrastructure like everyone else for our tanks. We're making our tanks bigger. We're putting them on rail cars. Our rail system's not designed to support them. We're getting calls and saying, can my rail support this load? And we need a way to measure the modulus or the strength of the track, just like we do with a fallen weight deflectometer or a heavyweight. And we don't need giant rail cars because we can't afford to have those to determine it. So we're looking for somebody to help us come up with something to be able to measure in situ track modulus so we can tell you right in a small section of track what's the load carrying capacity. So it's another big challenge as we continue to evolve our machines and our infrastructure, civil engineers, we're having to chase the vehicles. And I think we'll continue to do that throughout history. But we're so good at solving their problems, we always come through. What we do does matter. And I think just a lot of people don't really know it outside of our community. So keep up the good work. Thank you for your interest and thank you for your attention. And if you have any questions, I'd be happy to address them. All right. Questions? Yes, sir.
I have one question. What is an aircraft carrier's landing deck made of?
The aircraft carrier landing deck, I think, is made of steel from what I understand. And there was a question about maybe putting the aluminum planks over the deck to keep it from warping. Thank you. Yes, sir.
Do we have publicly available pavement design guides? Or?
Absolutely. There's a lot of information that we have. I would say most of our information is publicly available. When I want to find some of our stuff, sometimes I just go on Google Scholar and search for it. But a lot of the stuff is available. If there's anything specific, let me know. ERDIC has a library also. And so there's on the internet, you can get a link to the ERDIC library and search for information.
That was my also follow-up question. So do you allow your researchers to publish?
Absolutely. No, we encourage publication. Yeah, there's lots and lots and lots of information, journal articles out there that our folks, pretty much everything we do in pavements is publicly available. There's very few things that are limited distribution. So most of it's out there. So if you're searching for articles in pavements, you're probably finding some things by some of our researchers. Yes, sir.
Do you do studies on unconventional vehicles movement on water and land, like Mars rovers or something like that?
Can you say that one more time? Sorry.
Unconventional vehicles movement on land or water, like Mars rover or things like that.
So looking at movements, you're talking about vehicles that can operate on both land and water, or?
Can be, yeah.
Yeah. So we have a mobility systems branch, one of my sister branches, that really that looks at the vehicle mobility over that. For us in the pavements group, we look at how do you get a vehicle, say from a ship across a marshy area of shore, onto infrastructure. So a lot of that work is done also with matting or quickly rapid infrastructure. So we do that kind of work in ours. Does that answer your question?
Yeah, sort of. But a follow-up on that is, so if we are in an emergency case and we want to land the aircraft, let's say, and we have 2 days on land, what's the best way to do it?
So if we needed to land an aircraft and we had 2 days where we don't have any infrastructure?
Let's say we have enough infrastructure to do the things that we want. Other than matting.
We do have some matting?
No matting.
No matting?
No.
Oh goodness. Go somewhere else? That's always an option. Take somebody else's airfield, right? That's why we have a military. So we'll find one, take it if we want it. Right? That's probably the easiest answer. 2 days is pretty quick. I don't know, but if you can figure that out, we'd be happy to know about it. You know, you keep thinking it got the magic pixie dust I can just spray across the ground and it turns hard. And hey, maybe one day we can do that. Yes, sir.
What about bridge studies or fabricating bridges? Let's say maybe not for the Mississippi River, but I'm sure that sometimes the army or whatever have a problem to crossing one bridge, a river or something, a body of water, so they have to come out.
Yes,
in a way to do it.
A rapid way to do that? Yes, absolutely. We have a structural engineering branch, a structural mechanics branch that has a lot of work in bridging. And we are, in our pavements branch, actually we're doing a couple of projects for bridges. So the Army has large line of communication bridge. It's big, so it's like crossing the Mississippi River or something. So it's modular, it's prefabricated. You can go build a major bridge anywhere in the world once you ship the pieces there. We just used our HVS to do a deck wear study on that bridge. It was pretty cool. Also, the float ribbon bridge. So this is a bridge that floats in the water, and right now they have boats that go push upstream on it to hold it straight while your convoy's crossing. And there's these towers with cables. Very complicated, but we're helping work on making that bridge system a little simpler. Because the U.S. didn't design it, we actually copied that from some other nation. So now we're redesigning it. So yeah, there's float ribbon bridges. There's a lot of different military ways to rapidly stand up bridging across an area, but it still takes time. You still got to build a bridge. It's just we have all the parts pre-made and ready to do so. Yes, sir.
So since you guys work a lot on airfield payments, so based on your experience, can something be, is it something useful can be done for normal highway payments, some innovative?
Well, absolutely. Many of the applications, like I said, we're doing all these studies for like pavement preservation, we're doing the joint sealants, we're doing rapid setting materials for rapid repairs, which could be used in the highways. So a lot of the information that we'll get through our research, because there's a need for the military, can absolutely be used by the commercial sector to support, you know, just highway research.
But any like large scale application have been used on a highway payment?
I don't know the answer. I'm assuming the answer would be yes, but I don't know for sure. I can't think of an example offhand. Sorry about that, Dr. Arcadi.
For the F-35, during a recent visit I have like 3-4 years ago to Italy, they were using a material that we used 20 years ago, and I know that the Army Corps of Engineers follow up on that, which is hot mix asphalt with very open graded and filled it with cementitious material, special cementitious material. And I know that the Army Corps of Engineers, they use that for the abrasion from tanks and so on after that. Have you looked into this for the F-35? Because the people whom I talked to, they were from the Northern Command in Italy. Okay. And they were looking into that at that time, so I wasn't sure if it came from your group or you have been looking into this.
The group, there's a group out of the Navy, NAVFAC, that first started looking at pavements for F-35s, and I do know they looked at, they made a heat-resistant concrete design using Stahlite aggregates, and they were going to build a sacrificial layer, so every so often they'd go in and grind down like 1/8 of an inch or some material just to protect the coarse aggregate and from causing issues. And those were put in successfully at Eglin Air Force Base and one out in Arizona, and I think maybe some in California. I don't know about the flexible pavement, but that may be something that they looked at. The difference is the B variant of the F-35 is the only one that lands vertically. That's the one that's only operated on AM2 matting. All the other variants are short takeoff and landings, so they don't come straight down. I didn't realize that till recently. They still take off and land just in a short distance.
Right.
So, but all of them have what they call an IPP, integrated power something, plant something, but it puts an extreme temperature on the pavement, and that's what they're using the ones at Eglin and all that for. Just by having it there, it puts a lot of heat.
Right.
It's not that actual vertical operation, but the flexible one, I haven't heard of it, but some of our folks may have.
What's his name? Gary something, but I still have a sample. I can show it to you.
Oh, cool.
I kept a sample of that.
So yeah, there's certainly ways to mitigate that. It was just the pure vertical is the biggest challenge. Yes, sir.
I was wondering if, because the way I see it, the main difference one of the main difference would be how the aircraft transfer the load to the pavement.
Mm-hmm.
So my question is, what special considerations, if any, are considered for the way the military aircraft transfer the load to the pavement in the analysis and design?
Okay. So what's different about military aircraft and how they transfer load from the pavement through the pavement, and what's different in design? The difference in the military aircraft is just basically the weight and the tire pressures are extreme compared to commercial aircraft. So for an example, the one I have memorized, an F-15, for example, it has a 325 PSI tire. It's only 9 inches wide, and it's got 35,000 pounds single wheel load. You won't find that commercially. And so the issue is now you have to increase your thickness, right? Because you've got to have a higher modulus for that structure compared to what you would need for something with a lower tire pressure that you have more load distribution. So you got, I always tell folks that don't know much about the aircraft, I said there are two controlling aircraft in the U.S. military. You've got your F-15 that I was just describing, and you have your C-17 that had the picture of it landing on dirt. It has 6 wheels under a main gear. They are about 18-inch wide, well, they're 24-inch wide tires. They're 18-inch to contact. They're 142 PSI, and on those 6 wheels is 256,000 pounds. And so the difference between these two, your F-15 is your pizza cutter. So you imagine a pizza cutter going across the surface and just slicing and dicing your pavement. Really concentrated load. They don't see that in commercial. And the C-17 is your rolling pin. You know, you're rolling out your dough or something with just a big mass, and it's smushing and pushing everything out of its way. And so you've got, you know, subgrade controlling over here, right? You're going to tear your subgrade to pieces with this massive, big, giant, all these overlapping loads concentrating down deep. And over here, well, your load never gets down to your surface. It's just ripping apart your surface like crazy. And so you've got to have a really high modulus on the surface that won't bend and crack and destroy. So your Air Force pavements with fighter operations mostly have like 24-inch thick PCC pavements. That's big and wide. So that's kind of the difference is the commercial doesn't have that kind of a mass. And so you don't have to design for that kind of scenario, and they don't have that high tire pressure aircraft that's really going to tear up the surface. So your criteria is different, because we put loadings they're not going to see. Did that answer your question?
Yes, but again, like, but then how do you consider that distribution, that difference in distribution between these two during the analysis and design? It's just the constant pressure for a highway, just
it's the same concept. I mean, it's the same concept. It's just a different loading. So therefore, your criteria is different. But it's still layered elastic design procedure. You know, looking at how that load is distributed. It's just extreme. And so that's really the only difference. It's not a totally different procedure for evaluation or design.
Well, I think I was gonna say that there's a follow-up session because we exceeded our time. Maybe last question for
Okay,
Dr.
well,
Yes.
the C-17, is that the C-17 or C-5, the 6-wheel?
The C-17 is the C.
C-17, right? But one of the axles offset, it's the same
That's
dual
right.
tridem of the 777, or what FAA has been testing, right? In their facility, the same dual tridem, but one axle is offset kind of.
Yeah, one of them sticks out forward,
Yes.
and the spacing is not even the same between the tires. So yeah, it makes it even
So
very
from
complicated.
that point, I guess you guys have been some communication with the NAPTF and all the FAA testing of the gears. I know you're doing a lot of supply work or guidance and support work for FAA.
Yeah.
One thing I noticed that you mentioned geosynthetics and FAA. I'm not aware that they have started doing any geosynthetic testing. Maybe in this final cycle of construction cycle of testing, but has there been any work for FAA on geosynthetics?
I don't know the answer to that.
Yeah.
I know Greg Norwood and John Rushing are both our folks have been working very closely with them, we can ask them that question. I do know the stuff that we've been doing is on a small scale in the red box testing, and it's more of looking at, I believe that study's looking at placement depth. You put it at the top of the subgrade, you put it in the middle of the base, the bottom of the base, where's the best place to put the grid for the best benefit? Okay. And so that's one of the studies that we've been looking at for Dr. Brill.
All right, let's thank Dr. Rushing for the presentation. So announcements, Dr. Rushing will be here for another half an hour or so. If you want to stay and then follow up on this discussion, stay in this room for the meet and greet session.
All right, I know that.